Hey there, welcome back to Short Take 331. Today we're going to talk about another Fourier way to diffusion and waves. So if you recall our last couple of videos, we talked about diffusion and waves and the problem of solving the diffusion equation and the wave equation in one-dimensional settings using the Fourier transform. And our problem was set up on the whole real line, if you recall, and we took here in this diffusion equation the diffusion constant to be 1. And in the case of waves, we took in the wave equation 1 over c squared here, where c was the speed of light or the speed of sound or whatever wave you're dealing with. But here we're going to take c to 1 to have a unified approach and really draw parallels between the diffusion equation and the wave equation. And of course, we're going to have initial conditions. There's going to be an initial profile for our diffusion equation, which is just a function of x at time equals 0. And that's going to be our initial condition. That's enough to solve the diffusion equation. But in the case of waves, you need an initial profile and an initial velocity profile at time equals 0. So that's what I call here f prime. You should really say df dt if you want to be really rigorous at time equals 0. And in both cases, because these two equations are linear, we propose a Fourier decomposition of this form. Not only are they linear, of course, we're trying to solve them in the whole real line, and so the Fourier modes really make sense as a way to solve the problem, as we'll see. And the way this is different and more general in a sense than what we discussed in the previous two videos is that here we're going to propose a Fourier decomposition in space and in time. So we're going to have amplitudes f tilde of k omega and Fourier modes that are e to the I kx, so spatial Fourier modes, but there's also going to be a temporal Fourier mode, e to the minus I omega t. And we're going to be integrating over k and omega, of course. And so we're summing over all possible modes of this form, e to the I kx minus omega t. And so we'll have amplitudes associated with each k and with each omega, given by this f tilde of k omega. And of course, you can think of this f tilde of k omega as a Fourier transform in space and time of our function that we're trying to find, f of xt. Now, in the case of the diffusion equation, if you take this form and you submerge it into the diffusion equation, then you're going to get this equation right here, minus I omega f tilde from the first derivative with respect to time equal to minus k squared f tilde of k omega from the spatial derivatives. And that's the same, of course, that happened. This side certainly is the same thing that happened in our previous videos on the diffusion equation. And if you put these two things on the same side of the equation, you end up with this form, minus I omega plus k squared f tilde of k omega equal to 0. And what does this tell us? Well, this tells us that either f tilde of k omega is 0 everywhere, or somehow k squared is equal to I omega. And in reality, if you look closely at this equation, what this is telling us is that for all those points where this factor doesn't vanish, f tilde has to be 0. And so what we're looking for then is a solution that has this form, where f tilde of k omega is some function of k, which I'm going to call f0 of tilde of k, times the delta of omega plus I k squared. So this is the place where this part vanishes. And notice the way I'm writing this here, I'm putting the I attached to the k squared, so the sign here may throw you off, but if you multiply across this factor by I, then you get omega plus I k squared, which is what I wrote here as the argument of the delta. So this has to be this way, because otherwise the only solution to this is that f tilde is 0 everywhere, and the solution is just 0. Now, of course, 0 itself is in principle a solution to all our equations, but it may not obey the initial conditions, so it may very well actually not be a solution that we're looking for. And so we must have then that f tilde of k omega is a function of k times a delta where omega saturates at minus ik squared. So this is why I write this argument of the delta in this way. Delta of omega plus ik squared saturates when omega is equal to minus ik squared. Now, in the case of waves, you can carry through the same process, and you get two derivatives on the time side, and so you get minus I omega quantity squared, and then minus k squared on the spatial side. And so when you put all that together, you get this equation, which is the analog of the diffusion side that we saw here. So in the case of waves, we have then omega squared minus k squared times f tilde of k omega equal to 0. And that tells us that there must be two contributions at most to f tilde of k omega, where one saturates at omega equal to k, another one at omega equal to minus k, because that's when this vanishes. Everywhere else, f tilde of k omega has to be 0. And so we can separate those two factors and call them f1 of k and f2 of k. They don't have to be equal necessarily. and there will be in some cases depending on the initial conditions, but not in complete generality. They don't have to be equal. And so then we have that there's going to be f1 tilde of k times delta of omega minus k, and something else we call f2 tilde of k times delta of omega plus k. And so then if we go ahead and take our diffusion solution and insert it into our integral, we get that f of x comma t, so our solution is the double integral in k and omega of f0 tilde of k delta of omega plus ik squared e to the ikx e to the minus I omega t dk d omega. And we can regard this as a function of omega and go ahead and do the integral. And so if you do the integral over omega, then again this omega saturates, or this delta saturates when omega is equal to minus ik squared. And so we go ahead and we put that minus ik squared over here in omega. And if you do that, you have minus I times minus I is minus 1. And so you get minus k squared t, which is what appears here. So we do the integral over omega, and then we'll recover the diffusion behavior in time, which we saw in the previous videos on diffusion. In the end, our solution is an integral over minus infinity to infinity of the Fourier transform of this spatial profile at time equals 0. And then we have e to the minus k squared t e to the ikx dk. And so our job then is, given this f0 tilde of k, to do this integral, and then we obtain the solution for our problem at all times. And again, the time part is governed by this factor here. On the waves side, then we insert our solution that I wrote here in terms of f1 and f2, saturating at omega equal to k and omega equal to minus k, and you carry through the same process, and then you obtain a piece that moves to the right and a piece that moves to the left. And so then you have again, you do the integral over omega first, and then that saturates at, in this case, at omega equal to k, and the other one at omega equal to minus k. And so you obtain these two integrals separately, which capture the two possible directions in which the wave can move in this one-dimensional case. Now that's pretty much it. That's the generalization of the two approaches we saw in previous videos to solve the diffusion equation and the wave equation in 1D with given initial conditions. But now we've done it in perhaps a more elegant way, where we Fourier transform not only space but also time. And this, by the way, can be generalized to arbitrary dimension. Here we've been using these Fourier modes e to the ikx, e to the minus I omega t. But of course, in higher dimensions, you would generalize this to e to the ik dot r for the spatial part. The temporal part stays the same, by the way, and the spatial part can be generalized. For example, in 3D, we look at like this: k1x, k2y, k3z. And of course, if we're only doing 2D, then it would look just like this, just the first two terms. And if you're doing higher dimensions for whatever reason, maybe you're doing that in quantum field theory or for whatever application you're working with, then of course you would have more terms in these type of expression. Now, generally speaking, this type of approach will help you solve differential equations as long as the equations are linear. First of all, if the equations are not linear, then it doesn't make a lot of sense to use decomposition into Fourier modes. You can easily see that nonlinearities will start mixing different Fourier modes, and so these objects are not going to be eigenstates of your operator. And so it doesn't make a lot of sense to use this. Now, you should also always pay attention to the geometry of the problem. If the region of interest is not just a whole real line, if you have different boundary conditions that we've been using here, then you will have to use something else. In particular, if you look at our previous videos, you'll see that hard wall boundary conditions will quantize momentum, and so you will not have an integral over k, you will have a sum over discrete momenta or discrete modes, k sub n, which also can be generalized to 2D and 3D and so on, but it's different from the types of integrals we've been doing here in the past few videos on Fourier transforms. So again, here is the clarification. Our Fourier transform approach worked to solve these problems because the region was the whole real line. And of course, in all of these problems we've been seeing so far, there's no inhomogeneity. Our equations don't have any pieces that don't depend on the function we're trying to find, the function f. We have derivatives of f with respect to time, derivatives with respect to x or space in general, but we did not discuss a case where there's some inhomogeneity, some part that does not depend on f at all. There's just some function that is driving the system, and we will see that in future videos when we discuss more about Green's functions and such. For now, that's all I have for today. I hope you enjoyed this video. If you did, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. And I'll see you next time.